Last time we derived this equation here for q, which is a function of era, and in particular, if you recall, this function multiplied by e to the minus 1/2 times era was equal to chi of era, the function chi of era, which can be written as a function of phi of r, if you recall, and era is a function of r as well. It is linear with respect to r. So era and r are proportional to each other, linearly proportional. But we don't care about this now, we care about q of era. And if you recall also q of era, q of 0, so q of 0 is equal to 0. Okay, so we have to remember this, and we have to try to seek for a solution to that equation there. And that is not a trivial differential equation, because as I told you, it is not, so the coefficients here are not constants. So it is an ordinary differential equation. It is also linear, but the coefficients are not constants. And the same equation, a similar equation would hold for chi of era. But as you can see, something very similar happens here for the differential equation that q should satisfy. And we will seek for a solution of q for the differential equation, meaning that we want to find the solution q of era. We will seek for a solution in this form. So I will search for a power series. I will try to search for a power series that complies with that equation there. And what do I mean by a power series? Well, a power series is something like this. So I will search for a solution in this form. It's a summation from 0 to infinity of some coefficients c sub k times powers of era, so era k. But this is not this is still not good enough, because we also have to make sure that q of 0 is equal to 0 here. And if we use an expression like this, we have q of 0 is equal to c0, okay, which in principle might not be equal to 0. Therefore, I can multiply this expression by some power era, by some power of era to the power p. Let's say I will use p, but we don't know what p is, so we will have to find this. But for sure, p should be greater than 0, because if it is equal to 0, then of course we have this quantity here, and so we want to make sure that whatever is the value for c0, this quantity is equal to 0 when q of 0 is equal to 0. So we have to make sure that p is greater than 0. For example, it can be equal to 2, for example. Okay, so era squared, when we set era equal to 0, of course this function will be equal to 0. So we have to make sure that we comply with this condition here. Q of 0 should be equal to 0. And now, how do we make sure that this is a solution to our equation? Well, of course, we also have to find the right value of p, because we don't know that, but we have to substitute this expression into this differential equation, and then we have to see what happens. Okay, so this is the idea. We simply have to substitute it there. Now, I have to calculate the second derivative with respect to era of this function, but this is kind of straightforward, because it is simple to calculate derivatives of powers. So this can also be written like this. It's a sum from 0 to infinity of c sub k times era to the power k plus p. So we have to take the derivative of this coefficient, these terms here, and it is pretty straightforward to calculate. So the second derivative will be something like this. We have a sum from 0 to infinity of c sub k, and then I have to take the second derivative of this term. And when I take the derivative, I will have a factor of k plus p here, and when I take the second derivative, I will have k plus p minus 1 times era to the power k plus p minus 2. So the first derivative would be k plus p times eta to the k plus p minus 1. And then you take another derivative and you will have another factor here. And the exponent, we have to we have to subtract 1 from the exponent here. So we have a minus 2, which appears because of the second derivative. And then I will have minus the first derivative, so I have minus the sum from 0 to infinity c sub k times k plus p times eta to the k plus p minus 1. And then I have plus, I'm going to rewrite it below. I have minus, I have a factor of lambda here, and I also have to divide by eta, right? So I can try to put them inside the summation, and I can write it like this: sum from 0 to infinity of lambda, which is just a constant, so I could also factor it out from the summation, but I will write it inside the sum just for the sake of convenience. And then I have c sub k times eta to the k plus p minus 1, and this minus 1 comes from this factor of eta in the denominator here. And then I have minus sum from 0 to infinity of L times L plus 1 times C times Ck times eta to the power k plus p minus 2 equal to 0. Okay, so this is just how we can rewrite our differential equation. In this case, it is not a differential equation anymore, it is just an algebraic equation. It seems kind of complicated, right? But we can still work on this a little bit more. In particular, I want to rewrite this term here and also this term here as well. So I can let these two summations start from minus 1 instead of 0. And I have to modify them a little bit more. I have to change them a little bit more. In particular, the first one here will become sum over k from minus 1 to infinity, and then of course I have to replace k with k plus 1 here, because when I set k equal to minus 1 here, I should start from c0, because here I start from c0. And then here I will replace k by k plus 1, and then I have plus p, and here I will have k plus p, plus 1 minus 1, which is 0, of course. And then I have eta to the power k plus p minus 1, and then I have minus sum from 0 to infinity. So this will remain the same. I will not change that. C sub k, k plus p, eta to the power k plus p minus 1, and then I have plus, I have minus sum from 0 to infinity of lambda c sub k, eta to the power k plus p minus 1, and then I have minus the sum from minus 1 here, so I will let this summation start from minus 1, and I have to replace where I see the index k with k plus 1. So I have L times L plus 1, C sub k plus 1, eta to the power k plus p minus 1 equal to 0. And now let me do one more step. So these summations here so they start from minus 1, okay? So I can replace, I can rewrite this first summation like this. The first term will be C0 times P times P minus 1 times eta to the power P minus 2. And then I have plus the same summation from 0 to infinity of C sub k plus 1 times k plus 1 plus p times k plus p. And I can also factor out this term eta to the power k plus p minus 1, okay? And I can put this coefficient inside the first summation like this. So I have minus c sub k times k plus p And I can also put this coefficient inside the same summation. So I have minus lambda c sub k, and I also have minus this term here, so it's minus L times L plus 1 times C sub k plus 1, and then this will multiply eta to the power k plus p minus 1, but I also have another term which comes from this minus 1 here in this last summation. So I have plus minus, I have L times L plus 1 times C0 times eta to the power p minus 2, and this should be equal to 0. So this is our equation, which is very important, because we see that there are some terms that multiply these powers of eta. So in this summation here, this eta will start from eta to the power p minus 1, and then we will have eta to the power p plus 0, and then I will have eta to the power p plus 1, and so on and so forth. Okay, and the first term, the first coefficient is actually this one, which multiplies eta to the power p minus 2. And we have to set all those coefficients equal to 0, because this equation here should hold for every eta. Okay, it holds for every value of eta. Therefore, we have to set these coefficients here equal to 0. Okay, so the first coefficient that should be set equal to 0 is C0 times p minus 1 minus L times L plus 1 times C0. So it is this coefficient here, which multiplies eta to the power p minus 2. So this should be equal to 0, or maybe I could just put an equal sign here. This should be equal to that. And we have to make sure that this holds for every possible C0 here. And C0 is not defined, because it might depend on the boundary conditions of our problem. And in principle, we don't have to set this value here. So we have to consider this to be non-zero, and we can get rid of that. So we will not care about C0. But what this tells us, if you take a look at this expression, is that P, so this gives us the value for P. P should be equal to L plus 1. Simple as that, because if you replace L plus 1 here in place of P, you will exactly get that expression there. So P should be equal to L plus 1. Okay, whereas the other equation that we can get is, we will not use that, but you can get another equation from here, and this equation tells us that ck plus 1 times k plus 1 plus p times k plus p minus c sub k times k plus p minus lambda times c sub k minus L times L plus 1 c sub k plus 1 should be equal to 0. So this is true for k greater than or equal to 0. Okay, and it will give us a recursive relation which will help us, which can help us. We will not use that, but it can help us find the coefficients in terms of the previous coefficient. So we can write every coefficient. So we can write the coefficients in terms of C0 and the constant p, lambda, L, and so on and so forth. Okay, so the solution in principle can be determined up to a constant. Okay, but we don't need to search for. So we don't need to dig deeper and find the solution and explicitly. We still have to. So the important result here is this one. We want to try and analyze this result here. Okay, and now we have found that Q of eta can be written like this. It is eta to the power p, but p is equal to L plus 1 times the sum from 0 to its infinity here. So we have infinity, but I will tell you something more about this infinity here in a moment, of c sub k times era to the power k. Okay. Now you can see here that there's an infinity, and of course, if these coefficients were all of them were non-zero, well, this would be a problem because this summation would diverge. Here we have era to the power infinity, okay, and if era is greater than 1, that would diverge. Okay, so there exists some n prime, some index n prime, for which, let's say, above which the coefficient c sub n prime plus 1, for example, would be equal to 0. C sub n prime plus 2 would be equal to 0, and so on and so forth. C sub n prime plus dot dot dot, I don't know, plus 3 equal to 0, and so on and so forth. I can write it like this. Okay? And therefore, there should exist some integer n prime, like this, such that our summation will be truncated after that. Now, we can try to analyze the behavior of this expression when era is large. So we will do it next time, but this is very important. I will have to set up the problem. So if era is large, there will be a dominant term for q of era. So q of era will be dominated by era to the power l plus 1 times c sub n prime era n prime, because the other terms will be negligible. Okay, so this is the behavior of q of era when era is large, and this is a simple expression that we can plug into the differential equation. And now let me rewrite it here below. The differential equation for q is d squared q over d era squared minus dq over d era minus lambda over era plus L times L plus 1 divided by era squared times q equal to 0. We will consider eta to be very large, and therefore q will behave like this, and then we will substitute this expression there. So in place of q, and in place of q here, in place of q here. Okay, so we have to take the first derivative and the second derivative, and we will have to substitute this expression here. And we will see what that will imply. So we will find the discrete levels of the energy from doing this. Okay, so we'll do it next time.